Hey, welcome back. Now we're into triple integrals. So how do we do this? Well, we're taking the region underneath the surface and then filling it up with a bunch of little boxes. And each one of these boxes will have some sort of volume, something like change in x times change in y times change in z. And then if you sum all of those up, you basically get the volume, right? If you take the limit of this sum as the norm of these cubes or boxes goes to 0, and in this context, the norm is going to be the longest distance amongst all of the cubes through the diagonal of the cube. Okay, so taking the limit as that norm goes to 0, this will turn into, assuming we have a nicely behaved surface, it'll turn into the triple integral over the solid of, I guess, dv. Okay, it'll look like that, and that will give you the volume. On every box, you can also attach, though, a function. So, for example, this box right here, if I wanted to extract that and attach some sort of function, I get a different volume increment where I have the volume times some number based off of that point in space. Okay, so you'll have some f of x sub I, comma y sub I, comma z sub I times that thing. And then if we go and take the limit as the norm goes to 0 again of this sum, you get the triple integral over the solid q of the function f. Okay, so very similar to the double integrals. The actual application of these things may be a little awkward, especially with regards to changing the order of integration and handling how that changes the overall limits on the integral. Okay, so there'll be a couple problems in the homework where we have to interchange the dx, dy, dz. I'll look at some of those. I'll try to look at some of those. But anyways, to evaluate these things, you're going to work them as, again, iterated integrals. So we have this theorem 14.4, which is kind of like Fubini's theorem now, but for triple integrals. And the way I think of these triple integrals is surface to surface, then curve to curve, and then point to point. So surface to surface, surface 1 to surface 2, the bottom surface to the top surface. And if you change orientation, that becomes really weird. So you may be going from the left surface to the right surface, stuff like that, or back surface to front surface. And then you're looking at the projection of the surfaces onto like the XY plane or the YZ plane or the one of those planes. And then you're going curve to curve, so curve 1 to curve 2, and then point to point, point 1 to point 2. Okay, so being able to draw these things is definitely extremely helpful. You can always, go to our grapher in the Calc 3D grapher, whatever we called that, and kind of get an idea that way. But sometimes it's going, because you need to kind of think about the projections of these surfaces, that may not help a tremendous amount. Anyways, in the meantime, just evaluating a triple integral. Can you evaluate a triple integral? That's pretty easy. Let's look at problem, I guess, number 4 in the homework. So I got this triple integral now, 0 to 7 over y, 0 to y over 8, and then 0 to pi over 2. And then we have sine of y, dz, dx, dy. Okay. And for here, you don't even have to know, what it looks like or anything like that. They're just asking you to do some computations, so it's pretty simple at first. So anyways, the innermost integral, the integral of sine y with respect to z is z times sine y. And we're evaluating from 0 to 7 over y dx dy. Okay. So I get the double integral of apparently 7 over y sine y minus 0. Okay, so then dx dy. Okay. So with respect to x, that will be the double, and I'm integrating, so get rid of that integral. With respect to x, I just tack on an x, so it'd be 7 over y sine y times x, evaluated from 0 to y over 8 dy. And then finally, well, first still have to evaluate that at the antiderivative, so I have 7 over y sine y times y over 8, then minus 0 dy. Okay. So you could do a little bit of simplification. The y's here cancel, and you'll have you can factor out the constant 7/8. Then you have the integral of sine y dy, and of course the integral of sine y is just negative cosine y with respect to y, and then evaluate that from 0 to pi over 2. So that would be 7/8. Negative cosine of pi over 2 is just 0, and then minus negative cosine of 0 is just 1. So I'm going to end up with negative 1 times 7/8, which is positive 7/8. Okay, so no real big deal there. Just doing the integral. Okay, so these next set of problems have you setting up integrals and not even evaluating them. So setting them up is really half the battle, in my opinion. So let's take a look at, I guess, number 7. So the solid, they want to know, set up a triple integral for the volume of the solid, do not evaluate. So the solid bounded by the square root of 16 minus x squared minus y squared, and z equals 0. So z equals 0 is the xy plane. This guy over here, z equals square root, that's the upper hemisphere of a sphere. And if you don't like that, just looking at it and knowing it, you can always square both sides, rewrite it, and then do your trace analysis. So in the xy plane, that would just be a circle, and the yz plane, and sometimes you have to go through the analysis to figure out what the heck the thing is. It's all circles, so this is a big sphere. Okay, zx or xz, and because it's a square root, everything in the original function needs to be greater than or equal to 0. Okay, so this is going to turn out to be the upper hemisphere of a sphere. So if you drew that in the xyz plane, you would get, okay, so the base of it, when z is 0, you get x squared plus y squared equals 16. So that will be a circle with radius 4. So it'll look like this. And then you just want the upper hemisphere, so 2, 3, 4, you put that in a different color. It's just the top of it. Okay. Okay, and then again, z equals 0 is just the xy plane. Right. So the way you kind of think of this then with the triple integral, I'm oriented with the xy plane being the bottom. That's like the floor. Okay, so I'm going from surface to surface. The floor is, again, the xy plane. It's this circle right here in the xy plane. So that's z equals 0. So I'll say I'm going to go dz, dy, dx. So, and they tell you what to do for your order. Okay, so if you look over at number 7, they tell you it has to be in the order dz, dy, dx. Okay. And they even give you little hints, so it's not too difficult. We're not integrating any sort of function, we're just finding volume, so you could just put a 1 in there. And then it's surface to surface, blue surface to the red surface, right? So z equals 0 to z equals the square root of 16 minus x squared minus y squared. And then in the xy plane, you may want to zoom in on there and kind of look at the xy plane. Think about how you're going to do that, right? So this graph is given by the function x squared plus y squared equals 16. That's just when z is 0 in this formula here, right? So I'm integrating over this basically. So I already went surface to surface, I need to go curve to curve. So with respect to y, it's going to be y equals this half, which from our formula, solving for y, I would get y equals plus minus square root of 16 minus x squared. So the bottom half is negative square root 16 minus x squared. So negative square root 16 minus x squared, smushing that in. And then the top, the upper hemisphere, this part, the blue curve, is the positive square root version. Okay, so let me smoosh that in black here. So 16 minus x squared up top. And then for point to point, what are you doing? Well, you're going from here on the x-axis to here. And because it's a circle with radius 16, that will be from -4 to 4. Okay, so -4 to 4. But truthfully, it's always just surface to surface, curve to curve, point to point. So surface to surface, then curve to curve in the plane that the object is over top of. Okay. Okay. Let's look at another one. This one, number 8, is pretty crazy. I think this is one that's kind of crazy. The solid that is common interior below the sphere, x squared plus y squared plus z squared equals 80, and above the paraboloid, 1/2 z equals 1/2 x squared plus y squared. Okay, so let's take a look at our objects. So the paraboloid, let's kind of figure out what the heck this thing's going to look like, and I'm going to do the sort of the analysis via the traces again, like we did back in chapter or whatever. So letting z equal 0, we're in the xy plane. We'll have 0 equals x squared over 2 plus y squared over 2. And what is that? It's just a point. That's 0, 0, right? If we let z go positive, it'll be circles, right? So as we're going in the positive direction above the xy plane in the z direction, we're going to start getting bigger and bigger circles. Okay. When y is equal to 0, we get z equals 1/2 x squared. So in that case, it's a parabola like this. And you could already see how that's going to kind of affect this thing. It's going to be kind of, yeah, it's a elliptic paraboloid. And then when x is equal to 0, again, you get the z equals 1/2 y squared, so you get this picture. And putting it all together then, so we'll have in the xyz region here, we'll have sort of this parabola going in the x direction, there's a parabola going in the y direction, and then kind of circles zipping around on the on these things. Okay. And there's our kind of paraboloid. Trying to draw it the best I can. Okay, then the sphere, what the heck is the radius of that sphere, right? So the radius is going to be the square root of 80. Seems like 16 will go into there if I'm not mistaken. So that'll be 4 root 5 for our radius. And you know, at some point this paraboloid is going to hit into it and cut into the top of it. So we have some sort of sphere like this, and then inside of it you have this paraboloid, and it's going to eventually hit it and come out of it, and you have that kind of effect. Okay, hopefully that's vaguely clear. I don't know if I can usually make this look any better, but something like that, right? And then the X, Y, Z axes are like right here. Okay, okie dokie. Getting back then to the question, let's see if we're kind of on the right track. What are we trying to do? Set up a triple integral to find the volume of the solid. Do not evaluate the integral. The solid is a common interior below the sphere and above the paraboloid. Right, so at the end of the day, this region that we want is going to be kind of everything inside of the paraboloid, but then the top of the paraboloid is going to be the sphere part that is kind of poking its head out. Okay, so there's kind of the sphere portion is poking its head out the top of the paraboloid. Okay, so what? How are we going to deal with this issue as a triple integral then? Well, it's surface to surface, curve to curve, point to point, and I'm going to put the XY plane as kind of my floor surface, like the floor I'm standing on. Okay. In order to pull this off, I'm going to have to rewrite this surface in terms of X and Y. So sadly, I'm going to have a square root involved, and it'll be the square root of 80 minus x squared minus y squared. And so the bottom surface, the paraboloid, is the z equals 1/2 x squared plus y squared. And then the top surface up here is going to be that z equals square root of 80 minus x squared minus y squared. We really don't even need the lower part of the sphere, right? Because it's not intersecting with the paraboloid. Okay. So for the integral surface to surface, you're going from the paraboloid to the upper hemisphere of the circle. So it'd be 1/2 of x squared plus y squared to the square root of 80 minus x squared minus y squared. And again, we're only worried about volume, I think. So you just have one, and then I believe the order is dz, dy, dx. Let's see what the order they want. dz, dy, dx. Yep. Okay, so our next sort of goal is, what are we integrating over, right? So for this, you have to think of the projection of the solid object onto the floor. Okay, so if you projected it, basically what you're going to see is the sort of top edge where the paraboloid and the sphere intersect. That top edge is going to be kind of the projection into the XY plane. So I need a formula for that. And in order to get that, well, what is that? It's just going to be kind of the intersection of these two functions here. Okay. So what? Well, just set them equal to each other or do a substitution. Put z into here, or probably putting z into down here will work as well. All right. Okay, so let's do that. So I'm looking for the projection now, that blue thing, and I'm going to have to set these things equal or some variation. So I have the 1/2 x squared plus y squared on one side, and on the other side I have the z equals square root of, and this should be 80, not 8, 80 minus x squared minus y squared. So I just did a substitution into this guy right here. If you do a substitution into this other guy, you're just going to get the same thing except rearranged a little bit. Okay. Ultimately, I got to square both sides, so get 1/4 times what does it look like? It's going to be x to the 4th plus x to the 4th plus I don't know why this is so hard for me. 2x squared y squared plus y to the fourth. And that'll equal 80 minus x squared minus y squared. And then solving, I'm going to multiply both sides by 4. Seems like something's off. Let me pause and make sure. Yeah, I should have just went. All right, so first off, there's supposed to be a 0 there. Okay, let me fiddle around with this a little bit. This may look weird, but it'll get the job done. What do I have if I squared both sides? This will be x squared plus y squared, right? Squared. You kind of see on the other side there's an x squared plus y squared. Let's get rid of the 1/4 before we get around too much of it. Well, okay, so 1/4 x squared plus y squared equals 80 minus x squared plus y squared. See how there's another x squared plus y squared? It's quadratic in terms of x squared plus y squared. Okay, so let me now multiply by 4, and I'm going to move this stuff to the other side, set it equal to 0. So multiplying by 4, we get rid of the 1/4, x squared plus y squared squared. Add the other stuff to the other side. It's going to be 4 because I multiplied everything by 4. So y squared. And then minus 320 equals 0. Then you can factor this into x squared plus y squared. I guess minus 16, and then x squared plus y squared plus is 20, right? This part will never equal 0. There's no two numbers squared add together that will add the 20 and give you 0. So it must be that this other factor is equal to 0. X squared plus y squared minus 16 equals 0. In other words, x squared plus y squared is 16. The long way to go to get this stupid formula, but it would have been easier if I would have just approached the substitution in a different way. It would have been a lot easier, and probably when you do it, you would have chosen the correct poison, right? All right, so anyways, there's our region that we're integrating over. So going back to our integral, that blue curve is going to be x squared plus y squared equals 16. So if we're integrating with respect to y, secondly, I'm going to need y equals plus or minus square root of 16 minus x squared. So negative on the bottom. So again, it's like the bottom curve to top curve. So it's this region. The bottom curve is the negative square root part. The top curve is the positive square root part. So negative 16 minus x squared to positive square root 16 minus x squared. And then finally, on the last integral, you're going from negative 4 to 4. Okay, so sorry, I had to take a detour to get the answer. I couldn't believe it myself that thing's just equal. All right, do they make you evaluate? No, they don't want you to evaluate. Okay, great. This number 9, make sure you get it into the correct quadrant. They only want the octant. They only want the first octant. These problems now, changing order of integration, and you kind of really have to be good at visualizing. So when you go surface to surface, it's if they change the order of integration, they could change the like where is the base, where is the bottom. Okay, so in this problem here, they go ahead and you have to go ahead and sketch it. So number 10. So over a little bit, 0 to 7, negative 7 to 0, 0 to y squared, dz, dy, dx. Okay, so in the dz dy plane, z equals y squared is just a parabola. Okay, so if we extend that into the x direction, so look at the top part of that integral and the inner integral. It's going from z equals 0, which is the xy plane, to z equals y squared, which is basically just this parabola, but then kind of moved into the x direction, because x is allowed to vary over the real numbers. So your n thingamajig is kind of like a parabola on steroids, right? So it's this object here. Okay, great. So z equals 0 to that surface. So basically, we're kind of looking for the area underneath this thing. I'm not sure where exactly, but it would be kind of this wedge area underneath the parabola in here. Okay. Right. So anyways, the other bounds will tell you where. So -7 to 0. So actually, on the y-axis, you're going from here, like around -7, wherever the heck that is. So this is your y, this is your x, this is your z. So it's all this material underneath the parabola in that direction. Okay, so let me draw it again. Our parabola, we just care about this direction, right? So -7 is probably over here somewhere. So it's kind of like looking for the area underneath this parabola, this paraboloid shape thingamajig. And then on the x-axis from 0 to 7, right? So the area underneath this guy, from 0 to 7, okay? Let me make that curve a little nicer, like this. And we're looking for this wedge piece, the volume, not the area. Okay, so let's get rid of that stuff. So this point is at 7 on the x-axis. This is your y-axis. Okay, so looking over at the graphs, I gotta sneeze. Sorry. Looking at the graphs, it looks like it's, yeah, I already got it. So it's this guy here. They want you to change the order of integration then. And this is where it becomes kind of visually challenging. So if you're a good visual thinker, you should excel at this stuff. They want you to change it into dy, dz, dx. Okay, so your floor now is going to be the xy plane. Kind of redrawing it a little bit, the xy plane, or sorry, xz plane is the floor, would be kind of this right here. That would be your xz plane. I want to go from surface to surface, and so you're thinking if you project this object into the I guess I want to say I want to project it into the xz plane, but I don't think that's going to really do it. I mean, that's ultimately that's what you're going to be integrating over. But when you're talking surface to surface, the first surface over top of that red plane is going to be this surface in green, this kind of curled surface, and then the next surface is going to be the top surface. Let me put it in, I guess I'm running out of colors, yellow. So it'll be this surface over here behind stuff. So you're going, and actually it's the other way around, right? Because that's the negative direction. So you're going to be going from the yellow surface to the green surface in that direction. Okay, so the yellow surface is just a plane where y is -7. So you would go y is -7, and then going to this green thing, what the heck is that? And you need y equals something. Right now that green thing is given in terms of z, or it's terms of y, but you need it in terms of z, right? So the surface right now, the green surface, is z equals y squared. So you need to solve that surface for y, and you'll get y equals plus or minus square root of z. You got to be careful. You need the negative branch, right? Because you're on the negative side of the y-axis. So you need to go from -7 to negative square root of z. Okay. And then you can project to this red xz plane, and you're thinking on the z-axis, I'm going from I don't know. Well, the x-axis is easy. That's 0 to 7. For the z, then, curve the curve. I guess you could say, what the heck does it go up to? Is it on the other plane? Does it say? So it's basically where this yellow plane intersects the green plane. So again, the yellow plane is y equals -7, and the green plane was y equals negative square root of z. So if we set those equal to each other, we should be able to get the intersection, and that would tell us the z value that we need to integrate to. Okay. So setting these equal, -7 equals negative square root z, square both sides, you get z is 49. Okay, so 0 to 49. Okay, so it takes some hardcore art skills, but you know, when all else fails, you can kind of go to your Calc 3D and try to get the graphs that way. So again, where the heck is Calc Plot 3D? And go into here, and in this case, it was a z equals y squared. And you it'll plot it for you. You just have to be a little bit careful, because we only want that 1/2 over here in the negative portion, and the limits on the integral tell you that information. Okay. Then they probably want you to integrate the thing. I'll skip that part. Okay. How about this guy? Again, you're kind of what are we doing? Sketch the solid. Given by the integral. I think that one isn't so bad. These can be kind of nasty, right? These ones where we're finding all orders of integration. This first one, I think you're going to be able to do it. I'm hoping you'll be able to do it. So I'm going to go and look at the next one, number 13, which is a lot harder. Okay, so at least you'll have this in your notes. And then there's a couple applications. I'm going to put, you know, basically finding the center of the rotational inertia, the second moment of a solid, and then the first moment of a solid, which they're calling the centroid. Okay, so there's one or two of those. So let's look at number 13. I'm kind of debating, do I want to make this the video quiz? And I think I do. Okay, so let's make this the video quiz. I put that in my notes. I'm sure somebody very unimportant is calling me right now, but I don't have to wait. 14.6, and I'm looking at problem number 13. Okay. So first off, notice that x greater than 0, y greater than 0, z greater than 0 here on the right in problem 13. That means you're in the first quadrant. That's basically all that means. Anyways, let's look at our information, see if we can't get a graph. And you'll see this one's pretty nasty. Okay, they give you little hints throughout these integrals. You basically need 6 integrals, one for each order of integration. Okay, so let's first draw the thing. So I'm going from z equals 0 to z equals 8 minus y. So the projection into the yz plane, in that case z equals 0 is just the y-axis, and then z equals 8 minus y. So that has an intercept of 8 up here, and then it just, you know, goes down 1 over 1 all the way to 8 over here. Okay. And then you can extend that in the x direction. Okay, so extending that in this direction, and you just have this surface here in this first quadrant, and then dx, x equals 0 to x equals square root 64 minus y squared. So in your xy plane, then that will go from x equals 0 is the y-axis to x equals 64 minus y squared. Is that supposed to be a square root? No. Okay, whatever. X squared, or x equals 64 minus y squared. Okay. So it's a sideways parabola flipped upside down and then shifted over 64 places. So it's going to look like this. Okay. This point will be at 64, but it's going from 0 to that thing. So it's this region here that you're kind of integrating over. But then when you look at the y is going from 0 to 8, so it's only going to be this upper part of it. So in particular, this part. Okay. So in our picture, where is that? Well, it's going to be way out there, right? Because you have to go to 64. Well, it's way out here in this direction. So you go all the way up to 64. So maybe it'll give me a little more room over here. Little. Okay, so I'm like out here at 64, hopefully, and then the parabola is kind of moving through like this, and eventually it'll hit this guy and then kind of cut over like that. And you know, as it goes through, it's cutting through this region, so it's going to kind of go down like this for your surface. Okay. Okay. So yeah, kind of a weird thing. Let me make sure that this, does it really, where does it hit the y-axis, or the y-axis? What is this point right here? That's 8, so it's going to hit exactly at 8. So let me adjust this a little bit. It's going to go like this and then hit exactly there. So this red part, let me adjust that. And of course it's erasing everything now, so I have to regenerate my drawing. Okay, and then it's going like this, and then it's kind of intersecting like this. Okay, so I get this wedgy region thingamajig that I want to find the volume of. Okay. All right. I think that is the picture. I wonder if they give you a picture. They usually give you, they're nice enough to give you a picture. Yeah. So mine, it should be stretched. They've adjusted the X tick marks, so theirs is a smushed version of mine. Okay. Okay, great. So yeah, let's go at it. Getting all the different orders of integration. The hardest one is going to be where the XZ plane is your kind of base, right? This, I'm putting it in blue right now, XZ plane right here, using that as your floor. And it's because if you do the projection onto that XZ plane, you basically have this curve kind of going through it like that, right? So when you go surface to surface, there's really two surface to surface issues you got to deal with. Let me put it in, so the back surface is kind of this blue part, that's the floor, and then there's two surface to surfaces, so you're going to have two integrals. So let me do the first one yellow, surface to surface here, right? And then there's another surface to surface down in here, you see here to here, this other guy. Okay. So yeah, that is annoying. And like I said, you're going to need two integrals to deal with that issue. So let's delve into that issue. So the surfaces y, and then the dx dz and dz dx. We'll do dx dz first, and I'm going to need two integrals to pull this off. dy dz dx, right? Okay, right, so surface to surface, this surface right here on the top, You may want to start with the bottom one, right? That may be the more appropriate one to start with. This surface on the bottom here. Let's start with that one, right? So first you have y equals 0, which is that base. Okay, that's the back of this box here, right? That's this thing, that plane, and that's just y equals 0. Okay, so you can put a 0 on the bottom of that. Same for this other guy. Okay, and then you're worried about this, this surface right here that you're going to, right? So that surface is currently given as this x equals 64 minus y squared thingamajig, right? So x equals 64 minus y squared. I need it in terms of y though, right? So I'm going to solve for y. So y squared equals 64 minus x. And then y is plus or minus square root 64 minus x. I only need the positive branch though. And that would be that surface that I'm so interested in, right? 64 minus x. The other surface, kind of like this region here, which on the three-dimensional graph is this part, is just a plane. Currently the name of that plane is this 8 minus y, z equals 8 minus y, right? So I'm going to have to solve that for y. Z equals 8 minus y, so y equals 8 minus z, and that would be the second integral, right? Okay, and then it's just project this into the xz plane. I've already kind of done the projection right here that I just outlined in black. Okay, so I need to go curve the curve. So the first one I'm doing, I'll put red for this curve, and then, but it's with the x as orientation. So let me redraw this in our orientation here with x on the bottom and z on the top. So this is our x and this is our z, and it's going in a weird sort of way. If I project it, it's going to be going like this, okay? And then at 64, it's like right there. Okay, so this is 64, and this top number I believe is 8. So I need to go from x equals 0, this curve, to x equals, is that right? So for the first one, sorry, no, the first one is curve the curve for this stuff is this curve is first, right? And then you go to this curve. Okay, so it's going to be whatever the heck that curve, let me put it in blue, this curve here to this curve here. The second curve is clearly just 64, so I can go 64 at least on the top part, but that bottom part of the integral, I need the formula for that curve right there, and it's the projection into the xz plane of yeah, this is where it takes even me a little bit of brain power to pull this off, right? So it would be kind of a projection of where this function over here to the right, this guy kind of hits this guy into the x plane. So what I'm going to do is plug this guy into here and then solve for x, right? So I'd get the square root of 64 minus x equals 8 minus z. So this would be 64 minus x equals, I gotta solve for x. Well, that's fine then. 8 minus z squared. And so x is equal to 64 minus 8 minus z squared. So that would be this bottom limit, 64 minus 8 minus z squared to 64. And then in the y direction, clearly point to point is just 0 to 8. Okay. For the other portion of the curve, then the z So I didn't mean to get different order. This isn't a different order. This is the same integral basically. So this is still dx dz. For the other part, then I need to go from x equals 0 to x equals that 64 minus. So it's basically the other part. If you look on the xz plane to the right, or to the left rather, you're going from 0 to this curve, which we already found the equation for. So 0 to 64 minus 8 minus z squared. Okay, and then the last integral, z, again, is just going to go from 0 to 8. Okay, and then hopefully type that in, dy dx dz, dy dx, where are you? dy dx dz, that was the first one, so sweet. Well, there's a second one actually. Right. Let's make sure it's right. Yeah, if I FOIL this out, it's going to be the 16z minus z squared, I believe. This part right here is that right there. Okay, and then this other part. Whoops. Thank you. This other part right here that I just did, that integral is the second integral. So I have it in reverse order from what they put in the software. Okay, so that would be this integral. Just making sure it's correct. And yeah, okay. So that's one. You still have 1, 2, 3, 4 orders to go, right? So they give you one. I just found the second, and you need to do a couple more. The next easiest one though will be the dz dx, dy dz dx, right? Because you already have kind of the initial part, dz dx plus the triple integral dy dz dx. And so for the first guy, it'll have the same bound, 64 minus 8 minus z squared to square root surface to surface. And over here, 0 to 8 minus z. And then you're using a z formula, z equals something to z equals something, right? So here in the xz plane, you have this curve that you want to, you want to go from first curve the curve, so z equals 0 to whatever the heck that thing is, and we would have to go back to this formula here and solve for z, right? So that would be 8 minus z squared equals 64 minus x, and then square root both sides. 8 minus z equals square root 64 minus x, and then z equals 8 minus square root 64 minus x. So z goes from 0 to 8 minus square root of 64 minus x. This should be x right here as well. Then on the x-axis, of course, you're going from 0 to 64. And then you're going from this curve to this curve. So you go 8 minus square root of 64 minus x to 8. And then again 0 to 64. And that should give you the two hard integrals I sort of did for you there. Okay, and I'll let you do the other ones, are a lot simpler. I'll let you do those on your own, but I'm just making sure it's correct. dy dz dx, dy dz dx is right here. All this stuff, whoops. So right here, dy dz dx. So their second integral is my first integral, right? And it looks like I got it. Okay. Almost. I should be going from 0. Sorry, this should be 0. Yeah, And then the other one's right. I just accidentally rewrote because my stupid integrals are overlapping. Is that right now? Yeah. So these should challenge the heck out of you. They gave me nightmares. Not really, but you know, relative to some of the other problems, I thought these were quite challenging. But I mean, ultimately, it just comes down to your ability to do visual kind of representations, and then to think about projections into the kind of the basement, the floor, right? For the other projections, you can kind of see they're not going to have these. I think this is the only one like that where you had like two surfaces that you had to do the integral for. Okay. For these last problems, I would recommend just using the software, doing a computer integral. Yeah, and you should be able to bust those out using the formulas that are given in the book. So applications, I guess that would be the section. Did I give you a section 1? I didn't really even set up a section 1. So, I don't know. Section 2, applications. So the first one is the centroid issue again. So we want the balance point of solid regions now. So that it's good if you're like tossing an object into a spot, into a rotation of some sort, and you want to know what point that object's going to rotate about. That sort of kind of game. Anyways, the first kind of question you see there, and they're kind of in the wrong order. The centroid problem. You need the moment about the x-axis, the moment about the y-axis, and the moment about the z-axis. The moment about the x-axis is going to be the triple integral of x times rho of x, y, z. So you'll have some density function. And it kind of works the same way as what we saw in the previous section. Let me make sure I get these formulas correct before I start throwing them all over the place. Where are you? There. Yeah, so I guess they're not calling it moment about, they're moments about planes instead of axes now. So you'll have a moment about the YZ plane, and that will be given by some distance x. And then you'll have a moment about the XZ plane, that will be given by some distance y. And then you'll have moments about the other plane. So which moment am I? The XY plane, which is a distance z. And then your centroid, your sort of center of mass, x bar, y bar, z bar, is just going to be the ratio of these moments and the mass. And you find the mass, of course, just by finding the volume. The integral of the density function. So it's like density times volume. Okay, so over mass, and then mxz over the mass, and then mxy over the mass. Okay. Again, I would recommend using an integrator like Wolfram Alpha to do these. Yeah, I think that even in the question they say to do it that way. So int of whatever your function is, so rho, and then comma whatever your order of integration is. So usually z equals 0 to something, comma y equals 0 to something, comma x equals 0 to something, right? And then push enter, and you would get whatever the heck you need to get. So that's kind of the code that you would use for doing these. The other formulas then for the second moments, we have, so these are the first moments. The second moments, IX, IZ, are going to be, you can kind of get it from Pythagorean theorems and space, and I'm not going to draw that all out, but what you need for the moment of inertia about the x-axis is an x distance, and you would get that from like a triangle form, and then you use Pythagorean theorem, and the end result is this y squared plus z squared formula, and then times rho of x, y, z as usual, and then dv, and then I sub y is triple integral over the, whatever the solid is, q of x squared plus z squared, rho of x, y, z dv, and then you have your other formula there for the z-axis, and then there'll be gyration points as well. So rho of x, y, z dv, and the gyration points. See if they even give you that formula. Seems like it should just be the second moment about the square root of the second moment over mass. I guess they never really asked for it, do they? Okay, that's cool. Cool with me. You just kind of have to put these into your calculator. So for this one, it's pretty simple. Int of int of int, and each one is going from 0 to a. And so for ix, and I'm not even going to put that constant k in there because Wolfram will have a fit. So I go the other variable squared, y squared plus z squared, and then I should just be able to integrate that. Push enter, get the parentheses matched up, and multiply it by k, and you see I got it. And then if you want the I sub y, just replace y with x, and that would be 2a to the 5th over 3k. And then if you want I sub z, just replace z with y. You should get 2a to the 5th over 3. Yeah, that's what I'm getting. Okay, so just use the computer to figure out those integrals. And of course, using the computer is always a good way to kind of check your answers. Like in some of these triple integrals, they actually want you to evaluate the integral. I mean, it's so easy to make a little mistake that sometimes I'll just use the computer to check my answer. Like if I'm on my 4th try, I just use the computer to get the answer. If you already have the integral set up correctly, just use the calculator to solve that out. Okay, so anyways, that's enough for one day. Yeah, great. So thank you for watching as usual, and I'll see you next time.